Hello everyone. In this lecture, I'm going to start the open channel flows section. So open channel flows are flows where there is a free surface between the liquid and the gas, or water and air. So these are mostly the fluids that we investigate in civil engineering. For example, when you have a channel or a flume, this is where we have a free surface, a free interface between the water and air. Okay, so this is the definition of open channel flows. These are flows that occur in open channels, where the top of the channel is just removed, and we have the interface between a free surface between air and water. Okay. So the first thing I want to investigate in these open channel flows is what we call gravity waves. So gravity waves. And in particular, I'm going to focus on ripples, and let's see what are ripples. So ripples are small amplitude. Let me put this here. Small amplitude gravity waves. So we only focus on these small amplitude waves. Okay. So here, for example, you can see we have water. At the left, so we make small disturbance in a channel in a shallow. So here we make small disturbance in a shallow open channel flow. So we have a open channel flow here. We have water on top of the channel. The velocity of it is 0, it's steady. And then suddenly we make a small disturbance in this shallow open channel flow. Like disturbance could be, for example, you can put a stick here and then just shake it, or do some disturbance, okay? So what happens by disturbance is that here we will have a ripple that is formed, and then this ripple kind of moves toward the other side of the channel. So here, downstream of that disturbance, where that disturbance, it doesn't know anything about that disturbance yet, the depth of the channel is y, and upstream of the disturbance, the depth of the channel is y plus delta y. And in ripples, because these are small amplitude gravity waves that are moving, the requirement we have is that this delta y, the amplitude of this wave, over the depth of the water, the depth of the channel y, should be much smaller than 1. Right? It should be much smaller. It's a small amplitude wave compared to the depth of the channel. Okay. So now we want to analyze this flow, these ripples, and see whether we can find a formula for the speed of the wave, this gravity wave, this small amplitude gravity wave. So we can analyze this using a control volume approach. Okay, so let's see how we can do this. So we have it here. I'm gonna put it here. So here we are gonna use an innovative approach. I'm gonna talk about it, the way we are going to analyze this. The control volume that we are going to consider. So first, I'm going to talk about the traditional way of doing that, and then a new way that we are introducing here that we can do to simplify our equations. Okay. Okay. So let me also copy this. So in the traditional approach, what we would do is we have a we consider a fixed control volume in space, like, right? So something like this, steady, time invariant, control volume in space. Okay, this is our CV. Okay. So here, we have y plus delta y, and here the depth is y. Okay, so the velocity at this section is what? Is 0, right? Because the flow is not feeling anything about the disturbance. However, here we might have some velocity because of this disturbance, which we call it as delta V. And this is known as drift velocity. Drift velocity. Okay, so this is a kind of a traditional control volume. So here we have fixed control volume in space, but the flow is unsteady here, right? The flow is moving inside this control volume and is changing its shape. So this is the way we have it. And we know that this drift velocity is typically much smaller than the speed of the wave. Just so you know, this is much smaller than that. So if you want to do this, because this is unsteady flow, it's kind of complicated, but we can kind of simplify our approach if we define the CV differently. So the way I'm going to define the CV is that I'm going to define it as we are moving with this wave. So this CV is not a constant CV. It's actually moving with the wave speed c. So it's like you are on this wave. You are moving out over this wave. It's like there is an ocean wave, like those people who do surfing. It's like you are over that wave and you are moving with that wave. And then you want to kind of form a cultural volume around yourself as you are moving with that wave. So now let's see what's going to be the difference here. So Now, again, these heights are not going to vary. It's the same height. So the things that are gonna be different are velocities, because now we are moving with the wave. So moving with wave CV, control volume. So here, because we are moving with the wave, so the velocity of the wave to us should be 0, right? Because we are in the reference frame where we are moving with that, so we are not actually feeling the velocity of the wave. But on the other hand, what we are going to observe is that the downstream of the flow is actually moving towards us. So here we have a V which is equals to C, right? So it's not equal to 0 anymore, it's coming towards us. And on the other hand here, this is also going back toward the upstream is kind of, we are leaving that, so it's like it has a velocity of C minus delta V. In other words, if you want to simplify it, is just you subtract C from all these velocities here. So all the velocities that you have in a fixed CV, you subtract C, and then you are gonna get this. Okay? The velocities here. To simplify that. Now, so we are moving with wave CV. On the left, we had an unsteady flow, but now we are dealing with a steady flow, which is gonna make our analysis much more simpler. Okay, so the wave is stationary relative to yourself, but the water in front of the wave is coming at V equals to C towards you. Okay, so we are going to use this CV, this moving CV, to continue our analysis. Okay, so I'm going to write, I will first write continuity equation. So continuity. So the flow that comes in to this control volume should go out of this control volume. So the flow that comes in is here. So I write it down. C times Y, and then times the width. We are gonna assume that the width is constant. So I can write it down equals to the flow that goes out, so C minus delta V times Y plus delta Y times, again, the width of the channel, which is constant here, so I can just cancel these two out. And then I can expand this, so I'm going to get CY minus Y delta V plus C delta Y minus delta V delta Y. And because these delta V and delta Y's are pretty small, if we multiply them, they are going to be even much smaller than the other terms. So I can assume that this is very small and it's equals to 0 compared to the other terms. And also these two are going to cancel out. So what I am left with is this, y delta v equals to c delta y. And this is what continuity equation yields. Okay. So now let's write the other equation. And here, because we don't have any dissipation of energy, I can write the Bernoulli equation along the surface of this flow. And you know, because this is the surface line, and along this surface line, this is in the vicinity of the atmosphere. So the pressure of this is just equal to the atmospheric pressure, or PA, is constant everywhere. Okay? So along that line, I can write Bernoulli equation along the surface. So what we are going to get from section 1 and section 2, say this is section 1, and this is section 2. So we are going to get PA, atmospheric pressure, plus 1/2. And because the flow is moving that direction, I can, it doesn't matter, but I can write it like this. So rho, I can start from here. So I can say this is section 1 and this is section 2, because the flow is moving that direction. So 1/2 rho c square, this is velocity at here, plus rho gy equals to, again, to the atmospheric pressure at this section here, 2, plus 1/2 rho c minus delta v square, the velocity here, times y plus rho g y plus delta v, right? Plus rho g y plus delta y. So PA, atmospheric pressure, cancels out from both sides, and I am gonna get only these terms, and rho's are gonna also cancel out. So I am only left with these terms, 1/2 c squared plus gy equals to 1/2 c minus delta v squared plus gy plus delta y. So I'm going to expand these. So I have 1/2 c squared plus gy equals to 1/2 c squared minus 2 times 1/2 c delta v, which is going to be just c delta v, plus 1/2 delta v squared plus gy plus g delta y. Okay. So these two terms, 1/2 c squared, 1/2 c squared, are going to cancel out from both sides. And then gy's are going to also cancel out. And this term, because again, delta v is small, so if you, is very small compared to other terms. So if you square that, it's going to be even much smaller. So I can just neglect this. This is about 0. So what I get from the Bernoulli equation is this: c delta v equals to g delta y. Okay. So now we combine these two equations together. So combine two equations. So instead of delta V, I'm going to write C delta Y over Y here. So here I have the delta V is C delta Y over Y. So let me copy it here so we know we can better see that. So C, and then here I'm going to write this equation. So C times, instead of delta V, I write delta C delta Y over Y equals to G delta Y. So delta Y's are going to cancel out from both sides, and we get a very interesting formula, which is C squared equals to GY, or C equals to square root of GY. This is very important formula. And what C is the speed of this ripple, this small amplitude gravity wave. And we were able to show that the speed of that is just G times square root of G, the gravitational acceleration times Y, and that's why we call this a gravity wave, because this is driven by gravity. So the speed of a small amplitude gravity wave moving over the surface of shallow water is square root of GY. So you can actually measure this. It's interesting that you can actually measure this yourself and make sure that you get the same formula. So for example, if you fill a tank, or if you fill a sink or bathtub, say by a depth of 1 centimeter, so that it's kind of a shallow water, okay? So fill that with water, and then gently make a sponge drip into the water surface. In this situation, you will see some circular ripples, right? Like even in the lakes, you will see that circular ripples. So these circular ripples move at the speed of square root of GY, which if you calculate here for 1 centimeter is going to be around 0.3 meter per second. So you can actually measure this yourself and make sure that this relation holds. Also for tsunamis, which are very large and dangerous gravity waves that are occurred because of some earthquake over the ocean, you can simply calculate the speed of that tsunami wave with this relation, which is going to be a square root of G, where we can assume it's 10, times the depths of the ocean. So you can say where the earthquake occurred, the depths of the ocean, can assume it's around 4,000 meters. And this will give us a gravity wave speed of 200 meters per second. So the tsunamis they have very, very high speed and also high momentum as they approach the coast. Okay, so this was kind of an introduction to gravity waves and ripples. So in the next session, I'm going to talk about breaking waves and waves in a moving fluid. And then in the next lecture, we are going to talk about hydraulic jumps.